Okay, good morning, everybody. We now continue our discussion on the algorithmic method, and we have gone through this whole process that our methodology says that we will develop a recursive definition, have an inductive proof of correctness, analysis using recurrence relations, unfold the recurrence tree, examine the structures, try to optimize the split, then identify identical subproblems, and based on that, we remember past computation, and then we try to finalize the algorithm, which is equivalent to how we traverse the recursion tree. And there we also discussed pruning methods, and we came across that one of the key aspects is data structuring. Newer and newer data structures get developed so that we can remember past computation better for future use. And we have seen several techniques. Among the techniques that we have seen are divide and conquer, dynamic programming, greedy method, and branch and bound. In the divide and conquer is basically the recurrence equation, uh, how to balance the split, and second is how to ensure that identical subproblems are not solved multiple times. The greedy method tells us where in the choices of the recursion we can make a single irrevocable branch. Branch and bound tells us that during optimization problems, if we have a current best solution, how we can use bounds to prune away intermediate portions, knowing very well that the solution beyond that will not be better than the current best. And we saw several data structures that we had designed. One was the tournament data structure, which we said will evolve into a better data structure called a heap. We also saw our binary search evolve to a tree structure, which we call the binary search tree. So these are what are our evolving methodologies. And today we continue. We looked at search problems, and today we will continue to look at another class of divide and conquer problems and understand the divide and conquer methodology by solving sorting problems, much of which you may have already done earlier. Before that, I want to inform all of you to please inform your other classmates that there are people who are not attending class and they will be in deep trouble later on. So our methodology is as follows. Our methodology says that we have a recursive definition which has a base condition, and in the recursive condition there is a decomposition phase. I subdivided into, split it into two lists, etc., etc. Then there is a recursive call to each of these subphases. So I have broken it up into x into x1 to xk by a decomposition function. Then I call the recursive function in many ways, and then I get the results, and then I decide to recompose. And there are costs involved, recurrence equations involved, and we shall see how we achieve what we achieved. Just a quick recap. When we solved our search problems, where we did it especially in the tutorial class, we came across the fact that this sorted array, already sorted array, can be dynamically kept as a data structure called a binary search tree. And here, the dynamicity of the data structure enables us, where we only had in a pure array based structure, we had only the find operation. as we shall see, if we want to add the insert and the delete operation, then this binary search tree structure can be made effective. The advantage of the binary data structure is that the find part can be solved in what complexity? If it is sorted in an array?
Log n.
Log n.
Log n.
We want to ensure a similar structure where we did things in log n came up in which other data structure that we started discussing?
Heap.
Yeah, tournament and heap. Good. Now, when we insert elements into a binary search tree, then the tree can get skewed. But if the tree gets skewed, then our find operation may not be log n. So we will need to have a balancing operation, and we will study balanced binary search trees at some point in time, which are called height balanced binary search trees. And this will again, these are all data structures which are emerging for us. While they are standard data structures in computer science, in our methodology by which we are solving problems, they come as some things that is emerging out of the methodology. Now we move to sorting problems. So sorting problems, here we shall go through a mechanism by which we shall see several kinds of initial definitions. And we shall refine each of these initial definitions, and we shall come to the conclusion that if we do all the steps correctly, the eventual complexity and sometimes the eventual algorithm and data structures may be similar. The algorithm and data structures, even if they are not similar, the eventual complexity or the final version of all of them will be similar. So the exercise that we go through today is based a little on what we have already done, and we now show our methodology. So the first sorting method that we employ is sorting by max removal. Can anybody tell me what is sorting by max removal? But when I say this, what does it mean?
Like we find the max of
Removing the maximum number.
We find the maximum number, we remove it, then
And then find the
get
maximum again in the
that means
list
we
of the,
recursively call it.
yes.
Whatever we get, we compare these two, and that is our result. Correct?
Yes.
So we have to get our recursive definition. So here is our recursive definition. Our base case says, sorry, our base case says if L is less than equal to 1, return L. Then take the maximum of in the list L. We know how to find the maximum. Remove it. Call this sort 1 on L1 recursively. You will get the list M1. Put X where? In the beginning of the list. And therefore we will get the sorting in which order?
Descending.
We'll get it in descending order, or we'll get it in non-increasing order, because there may be duplicates. Complexity is straightforward. Tn equal to Tn minus 1, है ना? Tn is equal to Tn minus 1 plus order n. Therefore, it is an order n squared algorithm. By a straightforward method, if I use order n for finding the maximum. But all of us know that. So now, can anybody suggest how am I going to improve this?
Sir, we can use that heap data structure, sir.
Correct. That means now here I will use data structuring. I will use data structuring. That means I will now find this max, build a heap or tournament data structure while finding the max. So we will try to build a data structure which takes order n complexity to find the first max. And from the next max onwards, are we going to do it this way?
No, sir.
No, we will compare.
We will convert it to a data structuring operation. What was our guess? What was our main claim when we did the next max? If the first max can be found in order n time, the next max will be found in order
Log n.
Log n time.
log n time. Why? Because I will only compare
We
The
can
ones
backtrack
with
it.
which the max had 1.
the one which were defeated by the max. So I will convert this algorithm. My steps of algorithm design were final algorithm. How do I refine the final algorithm? Here, there is nothing to refine in the recurrence. There is nothing to change. There is no choice point. But here, I will move on to form a data structure, whether it's a tournament or a heap, after the first max. And then the rest of them will just be remove max, remove max, remove max, remove max, remove max. Is it clear to everybody? We have done this before. Clear, everybody? Anybody has a doubt? Good. So this algorithm will now become order n log n, isn't it? What is this n for?
Finding the first max.
First
Forming
max.
the
Maximum.
First max and
forming the heap.
making the heap or tournament. We will study the heap data structure in more details. And this is for the rest of it. Second onwards. And you see, we have eventually got an order n log n algorithm. So how do we now finalize our algorithm? Our new algorithm looks like this. If L is less than equal to 1, return L. Otherwise, find the first max and create the heap data structure to get heap. And then from I equal to 1 to L, go on removing one element and putting it at the end of the queue. This will give me my sorting in which order?
N log n.
N log n I know, but which order? If I put it at the end of the queue?
Descending. Descending.
Descending,
At the
ascending.
end of the queue.
It will be
End of
ascending,
the
right?
queue.
Ascending, sir.
Ascending.
Ascending order.
End of the
Ascending
queue.
order.
It will be in ascending. So you have now got the first flavor of taking our methodology from initial solution. There was not much refinement in the solution, but then we did a data structuring. That means while doing one of the operations, since we had many ways to do max, we did max in a particular way so that it makes it easy for the subsequent steps. So this gives us the first simplest way Till now, all of you must have known that if I write the max removal and then sort, max removal and sort, I will get an order n squared algorithm. But now you know how we can get an order n log n algorithm even by that method. Those methods, you had got those methods which were called, what were they called? What was that called which brought the max first out and then did the sorting? He wrote it in 2 iterative loops. What were the names of those?
Bubble sort.
Huh?
Bubble sort. Bubble sort.
This is not bubble sort. Bubble sort is slightly different.
So insertion sort.
This is not insertion sort. What is insertion sort?
So like oh sorry, insertion sort was I think finding
was
the
it mod
correct
sort
index
then?
of a random.
No. Find out what it was.
Selection sort.
In sorted
Selection
array
sort.
Okay.
Okay. Now let us go to another recursive definition. Anybody has a doubt here? Good. Now we come to the next sorting method. The next sorting method starts with a different recursive definition. What is the new recursive definition that we will employ? We have a list L equal to x1, x2, xn. We remove x1 or any xi. Remove any xi. L dash is equal to L minus xi. Then sort L dash, what will we get? Say y. Now what are we supposed to do?
Putting xi in the proper position,
Right.
in L dash.
Insert xi in y to get z. Correct? Is everybody with me? This is a new recursive definition. This is a new recursive definition. Anybody has a doubt? Abhishek Chaudhary, are you okay with this? Abhishek Chaudhary, are you okay with this? Are you there in the class? Jyotiraditya Aryan?
Yes, sir.
Is it clear?
Yes, sir.
What is the complexity of this algorithm just by this?
Insertion sort, it should be.
You tell me what is the recurrence equation? Tn?
Tn equals to, it would be,
T what? Tn minus 1 or
minus 1.
plus?
Then it is comparing, again calling. So it would be.
Remember, y is already
Sorted.
So if y is sorted, finding where xi is supposed to go.
Okay, that would be only one.
In one shot, you will find out where xi is supposed to go.
That would be log n.
Log n. So I can do log n. Now, where is the catch? If I apply binary search, where is the catch? I can find the position, but then
So we have to shift the values to insert.
we have to shift
Yes.
all the, see, if I find the position and I find that it is here, then I have to shift all these values, hai na? Mohit, is
Yes.
this what you're saying?
So, but we could
Exactly, sir.
just make a linked list and then use it to.
If you, okay, Ishan, very good point. If you make a linked list,
But we
then
cannot
if you make a linked
do-
list, can you apply binary search on a linked list?
No, sir. So have to traverse every time.
Wait, let Ishan get convinced. You're right. Rajdeep, you're right. I cannot do binary search on a linked list.
So binary search just depends on comparing with the middle index, right? So,
How will I know which is the middle index of a linked list?
oh, okay, yeah. For that, I would have to go from one node to another.
So I am now stuck between my search or find operation and I have to do an insertion operation. If I use linked list, insert operation after find is constant time. But find is no longer order log n. If I use an array, then my find is order log n, but now my insertion again becomes order n. So now I am stuck. And once I'm stuck here, what am I supposed to do? Can anybody suggest what am I supposed to do once I'm stuck here?
So probably search for a better data structure.
Correct. Look for a data structure which has got which operations? Find,
Insert and find.
and insert in order
Log n.
Login.
Login.
So now I have to find and insert in order log n time. Only then will my recurrence equation become Tn is equal to Tn minus 1 plus order log n, which will eventually give me order n log n. Jogu Bhanu Teja, are you with us here?
Yes, sir.
Karthik Sahu, you are all right. You were sick, you said?
Yes, sir, I'm better now, but
Okay.
I'm still feeling
Take
weak.
rest, take rest, take
Medication.
rest. Take rest, take rest. Manish Kumar Roy, is it clear?
Yes, sir. Hello. Yes, sir.
Yes. Good, good. So when we go to our recursive definition, we get to a situation where our base condition is same. Our decomposition function is order one time because we choose any element. We can choose the first element. Then our recursive condition is sort to L1. The question is insert. That means we are now to define a data structure which can do insert and find together. Find and insert in order log n time. And that data structure is a binary search tree. So how will you do a find operation in a binary search tree? Can anybody tell me a recursive definition?
So we will start from the
We'll compare.
top and
Start
then
from the root node. Compare it with the
If
root
it is
node.
equal to the element,
We'll return that.
So we stop.
we stop and return the pointer to that element.
yes, sir.
If it is less than the element, what do we
Go
do?
left.
Go
We'll
left
go to the
means
left
what?
side.
We recursively call it on the left child.
Yeah, recursive.
If it is greater, we recursively call it on the right child. And when do we stop?
Unless we hit a null node or we find
Yeah,
the
that means there is no child which I have to go to. That means suppose in this data structure, I ask you to insert 4. Then I look at 3. I will go left side or right side?
right side.
Right side.
Right side.
And then looking at 8, I'll go left or right?
Left.
Left.
And I will reach this position, which is null.
So we will insert 4 here.
So I am supposed to insert here. If I were to insert -3, where would I insert?
To the left of 1.
Mayank Baid, where would I insert -3? -3? Mayank Baid. Mihir Raj, where would I insert -3?
To the left of 1.
To the left of 1. Now what will happen if I insert -3, then I have to insert -2, then I have to insert -7. What will start happening?
Sir, the depth of the tree is increasing.
Correct. And that will put which of my choices into jeopardy?
Find.
My order log n will get into trouble, you know?
Yes.
Because
Yes,
it will
sir.
get skewed. So I need to have a balanced structure. So I need to create a binary search tree that after insertion again restructures itself so that the worst case height of the tree is order log n. And if it has to restructure itself, this restructuring also must be done in
Login.
within that
Login.
log n.
At least. Uh,
At most.
yes, at most. Sorry.
That restructuring also has to be done in at most log n time. And there is a data structure which we shall come to, a series of data structures which can do insert, delete, find, 3 operations. And keep the tree balanced. How would I delete an element from a binary search tree?
So we find it, and after removing it, see which child of it can be made the node.
Right. Which child of it would you make the node? If it has got 2 children. So let us revisit the problem. I want to do delete. I am in a binary search tree and I want to do delete. And
Sir,
I
if
have found the element. Suppose this is 18, this is 12, this is 24, this is 4, this is 15, this is. Can the value here be 12? Can the value here be 16 here?
No, sir.
No, sir.
So this value has to be 19, let us say, and this value let it be 29. Now I want to say delete 12. So I will come here. I have to remove 12. So what do I have to do if I have to delete 12?
To make 4
15 or
Either make
can be
4 or make 15. And the if I make 15 and 15 suppose had 2 children.
So
So I
then
have,
it's better to make 4 the child, the parent.
suppose
and
4 had another 5, 6 children.
It must be next greater element, sir.
Yeah, suppose I make next greater. So which one I have to put? I have to put here, very nice statement. Who said this? Repeat it again.
The next greatest element must be placed it at the node which we are deleting it.
So I have to find the next larger element than this. Is that what you're saying?
Yes, sir.
Is it now getting clear to everybody what I have to do?
Yes.
Yes, sir.
No, sir.
So like in the subtree of, in the left subtree of 12, we have to find the element that is in the rightmost position.
So now in a binary search tree, I have to replace. Can you repeat, Jyoti, once more what you said?
So in the left
No, that lady, I forgot her name.
Medha, sir. Medha.
Medha, can you tell once more what you want to do?
The next greatest element of 12, sir. Like the 15th left child.
Yeah. Right. So you want to get the next largest element or the previous element?
Next largest element, sir. So that the left child of 12 can also be satisfied.
Correct. So either you have, is it necessary to get the next larger element or the previous smaller element? Which one? Or any one of them?
So I am not being able to follow. Could you give an example just to make it clear?
Let me give you an example. Let me give you all an example. Are you seeing the new example that I am creating?
Yes, sir.
Ishan, is it clear now? Can you see the example? Everybody can see the example? Now I say delete 18. When I remove 18, which element will I replace 18 by?
So either 16 or 20.
Right. Now you got it?
Yes, sir. Yes, sir.
Now tell your friend who was telling us to replace it by 20. Is 16 also possible? Vedha?
Yes, sir.
That is also possible. So is it clear to everybody that if I have to remove this, then I can also do it by, so can I replace it by 12 or 24? While what we were trying, Rudra Jyoti?
No, sir, we cannot do that.
We cannot. So what we are trying was not correct. Correct? Is it okay?
Yes. Yes. Sir.
Now, how do you find either 20? What is the definition of 20? It is the smallest of right subtree, and 16 is the largest of
left subtree.
How much time does it take to find either of them?
Like if they are balanced, then it will take
Log n. In the left subtree, you go to the left subtree and go right. In the right subtree, you go to the right subtree and then go left. That's all, isn't it?
Yes.
So then once you replace it, then you may need to no guesses?
Balance the tree.
Balance the subtree.
You may need to. Nancy, what do you need to do? Nancy, are you there? Naman Jajani, are you there?
Yes, sir.
So what do you need to do? You may need
Balance
to
the subtree.
balance the subtree. Now, so what operations can we, if the tree is balanced, what operations can we do? We can do find, we can do insert, we can do delete, Then what else we can do? Find max, find min, isn't it?
Yes, sir.
If we have a balanced binary search tree, we can do so many operations. So now we know that what we can do in our insertion sort, the way we did insertion sort, this insert now we can do in how much time?
Log
Log
n.
n time.
Login.
So we can do this insert in log n time. And if we can do this insert in log n time, what happens to our final algorithm?
N log
So
n.
it becomes n log n.
What happens? How does our final algorithm look like?
So its order becomes n log n.
It order becomes n log n, but now all this recursion that we had when we finalize the algorithm, what happens to the algorithm?
That every level of recursion, it will be a log n.
All that is true. Now, after I have understood all this, I have created my binary search tree data structure. Finally, my final algorithm looks like what? Does it need to have any more recursion? It needs to have only one for loop. And that for loop will do what?
So one by one insert the elements into the tree.
Exactly. For I equal to create a null binary search tree. For I equal to 1 to L, remove xi from L, insert. Remove, insert. Just insert one after another.
Yes.
Got it?
Yes, sir.
So finally at the end, your final algorithm has nothing else to do. What is your final algorithm? Your final algorithm for insertion sort ends up like this. Can anybody tell me? You has B equal to empty BST. For each xi in L, do what?
Remove xi from L and add it to the binary tree.
Insert
xi into L. Into B, sorry.
Have you realized all your insertion sort algorithm finally ends in this? Mohammad Gurfan Ansari, are you with us? Naveen Sani, are you with us?
Yes, sir.
Got it, na? How
Sir.
we started from that insertion definition, we realized we have to convert this to a data structure where insert and find. Find and insert. Find if it exists and insert if it does not exist. If it exists and there are duplicate elements, what will you do to the data structure? Can you tell me? Naveen?
Sir, could you repeat?
Have you understood what we are doing or have you not understood till now?
Sir,
Are you lost?
sir, not completely, but I'm understanding.
Have you understood this recursive definition of insertion sort? Did you understand what we discussed here in this box? Can you explain to me what we discussed? What is
Yes,
written?
sir.
L,
Yeah.
remove
Means we
xi.
find the we find the maximum and we
maximum. This is not the maximum. This is insertion sort. That was a different problem. This is the slide here written maximum. You're just trying to say something. See, if you have not understood, you did not hear, you're not paying attention, tell us. If you waste our time by trying to give me some gappa, remember that, I have 35, 40 years of teaching experience. Don't give gappa. I'm here to teach you. If you don't understand, ask. If you're sleeping, say I was sleeping. That's all right. Have you understood this box? Did you pay attention to what we were saying? What is the point scolding you? You all are all 20-year-old, 19-year-old, 18-year-old guys. Have you understood, Naveen? Did you pay attention to what I was saying?
No, sir.
Okay.
I didn't understand.
Read it. Yeah. Did you pay attention what I was saying here?
Yes, sir.
Then what is the L?
It's a list.
Then what is remove
list of
xi?
elements. Remove means we will remove any element xi.
Right. And then what is this y equal to sort L dashed?
L dash is the new list and we sort it.
And then what is this?
Then we means to the L dash we insert the removed element.
So how
to the sorted list L dash means to
sorted
y. Yeah.
List y. Good,
yeah.
Good. Now you are not paying. Now you are paying attention. You are all intelligent people. Once you pay attention, it should take you 2 minutes to understand. So how will I insert this element into this sorted list? What is the method to do that? I must do it in how much time?
Login.
Login. How will I do it in login time? That is when we came to this binary search tree data structure. That is when we came to this binary search tree data structure. You know what is a binary search tree?
Sir, it goes like smaller this side and larger in the
that side. Very good. So if I have to find an element in a binary search tree, suppose I have to find 17. Where will I go?
First, because 17 is less than 18 to the left side.
And then?
Then 17 is larger than 12, so to the right side.
Then
it stops because there is no more.
It tries to go to which side?
To the right side.
And if I have to insert 17, this is its correct position, hai na?
Yes.
So now I can find and insert an element in order of height of the tree. Got it?
Yeah, yes, sir.
And this height of the tree is supposed to be how much?
Login.
The problem occurs that if I don't restructure the tree, then if after 17, if I give 17.5 and then I give 17.75, then I give 17.775, then the tree will go on becoming longer in one direction.
Yes,
so
sir.
I need to do
balancing.
We will study balancing later on. Let us assume we know how to do balancing.
Yeah.
Then we are discussing, now I can do find, I can do insert. We also discuss how I can do delete. And while doing delete, we discovered that I can also do find max and find min.
Yeah, yes, sir.
So now we have this fantastic data structure wherein log n step, where n is the elements of the binary search tree, I can do each of these operations, one operation in log n time. Once I can do that, now my algorithm for insertion sort becomes what? I'll take one element from the list, insert, another element, insert, another element, insert, another element, insert, isn't it?
Yes, sir.
So this becomes, what is the complexity of this algorithm now? Order?
N log n.
And login.
When you first studied insertion sort in coding, you may not have imagined that it can be transformed like this, isn't it? All of you?
Yes, yes, sir.
Why did it come? Because we used our method. We used our method. And then we shall see, as we come to more and more complex problems, that how useful this method is. Now tell me, if I have duplicate elements, anybody tell me what to do?
So we can first find xi and b, and that is going to take like equal amount of time, because either way we need to find the position where we are going to insert. And then if there's an element which is equal to xi, we just continue with the next iteration instead of inserting it.
No. When we have to list out all the elements, then if I don't keep track of how many I have of a particular value, so all I need to do, Aditri, is to keep a counter with every node, which will tell me how many elements are there. Have you got it? So if I find that element and I have to insert another of the same number, I just increment the counter by 1.
So can we also like put it in the parent of that? Suppose like we encounter 24 once again, then can we put 24 as the parent of 24?
You have to insert 24, assume 24. You either assume 24 is 24 plus epsilon, or you assume 24 is 24 minus epsilon and insert it. So if you assume 24, you assume it as the parent of 24. Where will you put this 24? You have to put this 24 somewhere. No? You have to make it now the right child of 20. That is your problem. You will end up in more problem. Better to keep a counter.
Yes.
Now, what else can you do with this data structure? After you have inserted all the elements, how will you print it in sorted order? You have inserted everything. This is fine, but where do I get it in sorted order?
So we go down completely, we print, then we go up one step, and then come down again. So like we
So
first
we can recursively call print on the left and then print the current node, and then recursively call print on the right one.
Correct. So very good. Listen very carefully about what he said. You recursively call like this. Print, if I have to write print, in which order you want to print, ascending or descending?
Ascending.
Ascending, and you'll give the binary search tree root B. Then what will you, how will you call it?
Print ascending, B left
Print
subtree
ascending,
of B.
the left B. So let me write it neatly somewhere. So can you all see? Print ascending B. You will call it, what is the base condition?
If the
B equal to
null, then parents in null, then just return.
If B is not null, then you do all this. Correct?
Yes.
If B is not null, you write what? Print ascending B dot left, print node
B data.
Yeah, print the node. Print node dot data.
Yes, sir. And then
and then B dot right.
ascending B
right.
Ascending B right. Okay.
Yes, sir.
Neat, isn't it?
Yes, sir.
Pooja Sharma? Pooja? Rahul Das? Ritam Talukdar?
Yes, sir. Yes, sir.
Clear?
Yes, sir. Yes,
How
sir.
much
It's
is the
in order.
complexity, Ritam, of this?
O login. We'll go to print. It will okay. TN X TN X.
Arey Baba, every node is visited only once.
Okay. Yes, sir. Yes, sir. Oh, okay. Okay, sir. ON. Okay. Correct, sir. Correct.
And if you want to print in descending order, you just replace right by left. You first do right
Correct.
and then do left.
Yes, sir.
You first do right and then do left. These are called traversals of trees. You remember you all did in order, pre-order,
Yes, sir. In order
post-order.
traversal. Yes, sir. Yes, sir.
You all had done all in order. Ritik Prabhakar? Are you there? Ritik? Samira Yasmin? Samira Yasmin? Are you there?
Excuse me,
Shanmukha?
sir.
Yes.
So can you please explain this print part with an example, sir?
Take this example. You've
Yes,
got
sir.
this example, hai na?
Yes, sir.
So it will call it at this point, at the root.
Yes, sir.
The root is not null, so your first thing is it will go to the left.
Yes, sir.
This is not null, it will go to the left.
Yes, sir.
Its left child is null, so it will back off.
Yes, sir.
Then it will print this node.
Yes, sir.
Then it will go to the right. Right is null, so it will back off.
Yes, sir.
Then it will go back here. It will print this because my algorithm is print left, print node, print right.
Okay. Yes, sir.
Then it will come to this.
Yes, sir.
This is not null, so it will go left. This is null, it will come back here, print 16. Then it will go to the right, go to 17. 17 left, right is null, so it will print 17. It will
Okay,
now
got
next, which one will be printed? Tell me.
Now after 17, because
It
again
will
the
go
left
back,
part.
16 is done,
Yes,
12
sir.
is done. It will go back here,
Yes.
isn't it?
Yes, sir.
And it will print?
It will go right this time.
No, but it will print the node 18.
Oh, right.
Na?
Yes, sir. Yes, sir. It will print 18.
So now you are clear how it is coming.
Yes, sir. Got it. Thank you, sir.
Very good. So we'll stop today. What we have done is, while we had this traditional algorithms of maximum selection sort, insertion sort, we discovered two new data structures, tournament heap and binary search tree. And now we see that this binary search tree can do many things. And we simplified both our algorithms to simple iterative algorithms. The first one was make the heap and start removing one by one. The second one was insert one by one and then just print in ascending order or descending order, whichever you want. So this is our methodology. This is our methodology. Are you now getting the fun of the methodology?
Yes, sir.
That these two algorithms you knew. But even though you knew these two algorithms, you did not take it to the last step. And once you take it to the last step, we will see that in many cases, whichever way you go get the initial definition, not in all cases, whichever way you get the initial definition, you will eventually come to a final algorithm whose complexity is equivalent whose data structure is new, etc., etc. We will continue tomorrow and have
Excuse me,
more
sir.
fun. Yes.
Sir, like when you're telling these algorithms, like are we also expected to like learn the actual like how we code, like for example, a binary search tree and like
Yes,
the
yes,
new
we
data
will
structure?
learn. We have not come to that. We will come to that. Yeah, we will learn. So we have kept it in stock. How to code, how to write. So you have to learn how to code all these things eventually. But now we know at least the pseudocode of doing all this. And the
Yes.
pseudocode for doing all these we will do in more detail. Both tournament heap and binary search tree, balanced binary search tree, we will do in more detail. We now know that we have discovered these two. Though they are all textbook algorithms, we discovered it.
Yes, sir. Thank you, sir.
Any other questions? Recording can be stopped.